Hello, I'm Dave Brown. Today we take up Chapter 5 of Solid-State Electronics, which is titled Amplifier Applications. So far, we have biased the transistor by using two batteries. However, transistors can also be properly biased with only one battery. It is easier to understand the proper bias conditions when two batteries are used, but in most practical circuits, the bias conditions are obtained by using only one battery. We'll now look at the three transistor amplifiers with the bias obtained from one battery. This is the circuit for a common base amplifier using one battery to provide the bias. The voltage divider, consisting of resistors R3 and R4, will make the base more negative than the emitter, so the emitter-base junction will be forward biased. The base collector junction will be reverse biased, since the negative terminal is connected to the collector and the positive terminal to the base. This is the circuit for a common emitter amplifier, using one battery to provide the bias. The current flow from the emitter to the collector will cause a voltage to be developed in the transistor due to its internal construction. This voltage that is developed will provide the proper polarity to provide forward bias to the emitter-base junction. The base collector junction is reverse biased in the usual way. This is the circuit diagram for a common collector amplifier using one battery to provide the proper bias conditions. The base collector junction is reverse biased in the usual way, while the emitter-base junction is forward biased internally in the same way as in the common emitter amplifier. A power supply like the ones in the program on rectifiers and power supplies is often used instead of a battery to supply the bias voltages. On circuit diagrams, the battery or power supply is often not drawn in, but instead terminals marked plus and minus are shown. This indicates that the plus terminal of the battery or power supply would be connected to the plus terminal on the circuit, and the minus terminal of the battery or power supply connected to the minus terminal on the circuit. We have seen how three different transistor amplifier configurations operate and how they are biased for proper operation. Remember, the names of these are the common base, common emitter, and common collector amplifiers. Okay, you're wondering, how can these transistor amplifier circuits be used for a practical application? Well, transistor amplifiers can be used anytime there is a need to increase the signal voltage from a small voltage to a large voltage, or from a small power to a larger power. Some common everyday applications are phonograph or stereo amplifiers. As the needle moves in the groove of the record, a very, very small electrical signal is generated by the phonograph pickup. This signal is much too small to drive a loudspeaker or even a set of headphones, so the signal must be increased or amplified in voltage and power before the music can be heard through the speaker. Transistor amplifiers are ideal for this purpose. Other uses are to amplify the signal generated by a microphone so it can be heard over a public address system at a football game or political rally. The radio frequency signals received by our radios and television sets must be greatly amplified before they can be converted into the audio and video signal which we hear and see. The signal from the radio may have traveled several hundred miles through the atmosphere by the time the signal reaches your radio. It is extremely weak and must be amplified many times before it is strong enough to operate a speaker. In industrial applications, a temperature transducer is a device which generates a small electrical signal with changes in temperature. The electrical signal is very small and must be amplified before the temperature reading can be displayed. Other units may amplify the signal and then record it on a strip chart recorder. The same signal may be amplified and used to drive an electric motor or a valve to control a process in a plant. Transistor amplifiers are generally divided into two classes: small signal amplifiers and large signal amplifiers. If the power dissipated in the transistor is greater than 1/2 watt, it is a large signal amplifier. If the power is less than 1/2 watt, it is a small signal amplifier. In a transistor radio, all the amplifier stages except the final output stage are small signal amplifiers. The output stage, which drives the speaker, is a large signal transistor amplifier. We will look at some small signal amplifiers first, then large signal amplifiers. In the tape on transistor amplifiers, you saw how the transistor amplified a DC, or direct current, signal. A small change in the DC current at the base of the transistor in a common emitter amplifier would cause a large change in the current through the transistor, and hence a large change in the current through the load resistor, and thus a corresponding change in the voltage drop across the load resistor. This we call amplification. If a small AC, or alternating current, is applied to the base emitter junction, then the transistor will amplify this signal, and a larger AC signal will appear at the output. In many applications, we are interested in amplified audio signal. Audio signals are AC signals, which can be heard by the human ear. Audio frequencies are usually considered to be from 20 hertz, or 20 cycles per second, to 20,000 hertz, or 20,000 cycles per second. The human voice and music are examples of audio frequency signals. Let's say we take a small audio signal from the pickup of a record player and amplify it. As it comes from the pickup, the signal will be very, very small, in the order of 30 millivolts, or 0.030 volts. This signal must be amplified to several watts to drive a speaker. A single transistor amplifier will not provide sufficient amplification. How do we get a greater amplification? We just add more stages of amplification. We take our one transistor amplifier, like this, and then connect another transistor amplifier to its output. The input of the second amplifier is connected to the output of the first amplifier. If both amplifiers have a voltage gain of 100, then the voltage gain of the two connected together, one after the other, is 100 times 100, which gives us a gain of 10,000. This is called cascading amplifiers. However, we must be careful when we connect transistor amplifiers in cascade. You will recall from the chapter on transistor amplifiers that the transistor must be biased properly if it is to amplify. The biased voltages on each of the transistors will affect the operation of the other stages of the amplifier. To prevent this from happening, a capacitor is placed between the two stages like this. This is called a coupling capacitor. Alternating current will pass through a capacitor, but direct current won't. The coupling capacitor will couple the audio signal, which is a form of AC, from the output of the first stage to the input of the second stage. At the same time, it will keep the DC bias voltages of the two stages separated. Cascading amplifiers is not limited to two amplifiers. Several amplifiers can be connected in cascade if necessary to provide sufficient gain. In fact, in most audio systems, such as stereo systems or public address systems, several transistor amplifier stages are connected in cascade. We have seen how a capacitor is used to couple two transistor amplifiers. Now let's look at another use of a capacitor in an amplifier circuit. If we have a common emitter amplifier, like this one, with an AC or audio input signal, the output signal will be divided between the load resistor, R sub L, and the emitter bias resistor, R sub E. This is usually undesirable, since we want all the output signal to be across R sub L. However, the emitter resistor can't be eliminated, since it is a necessary part of the DC bias circuit. We can eliminate the AC voltage drop across the emitter resistor by connecting a capacitor across the emitter resistor like this. Since a capacitor will conduct alternating current, or AC, no AC or audio signal will be developed across the emitter resistor, and all the AC or audio output voltage will appear across the load resistor, R sub L. Since the capacitor will not conduct direct current, or DC, the DC bias voltages are not affected by the capacitor across the emitter resistor. Earlier, we said there were two classes of transistor amplifiers: small signal amplifiers and large signal amplifiers. Up to now, we have been concerned with small signal amplifiers. Now, let us turn our attention to large signal amplifiers. These are the amplifiers which drive the speaker in a radio or television set, or the motor in an industrial control circuit. Large signal amplifiers are called power amplifiers, and the transistors used in them are called power transistors. These transistor amplifiers must deliver power from 1/2 watt to hundreds of watts. The transistors are larger, and since they are handling more power, provision must be made to cool them, or to conduct the heat away from the transistors. We do this with heat sinks, as we demonstrated in Chapter 3. Power amplifiers are divided into three classes: Class A amplifiers, Class B amplifiers, and Class C amplifiers. We will now look at each of these classes. First, let's take a look at Class A amplifiers. If we apply an AC sine wave signal into the amplifier input, we will get an amplified sine wave out. The output waveform will be like the input, except for being a higher voltage and power. The definition of a Class A amplifier is one that is biased so that current flows throughout the entire cycle. As you see, if we put a sine wave in, we get a sine wave out. Most small signal amplifiers and many power amplifiers are Class A amplifiers. Class A amplifiers are the most linear of the three types. They also have lower output power ratings and are the least efficient of the three. Most small transistor radios and AC-DC radios have a Class A single transistor output stage. Class B amplifiers require two transistors in a push-pull circuit. The requirement for two transistors is a disadvantage when compared to the single transistor Class A amplifier. However, this is more than offset by the greater power capabilities and much better efficiency of operation. Remember, in Class A amplifiers, if we put a sine wave in, we get a sine wave out. In Class B amplifiers, the transistors are biased so that current will flow only during 1/2 of the cycle. If we put an AC sine wave in, we will get an amplified output wave only during 1/2 of the cycle, like this. This is no problem, though, since we have 2 transistors in a Class B amplifier. The second transistor is biased so that it conducts during the other half cycle, like this. We now have 2 amplified half cycles, so we combine them to obtain an amplified signal, which is like the input signal. In Class B amplifiers, the output current in each transistor flows for 1/2 cycle, or 180 degrees. This permits a higher output power and greater efficiency than in the Class A amplifier, but slightly more distortion will be present in the output signal. The distortion can be minimized by careful design and usually does not create a problem. This is a circuit diagram for Class B push-pull amplifiers. These amplifiers are usually transformer coupled. Class B amplifiers are used as the output stages of most stereo systems, public address systems, and in many industrial control systems. Class C amplifiers are the most efficient of all power amplifiers. However, Class C amplifiers have some severe limitations to their use. Class C amplifiers are biased so that they conduct during less than 1/2 of the input cycle. In order to restore the output signal to a sine wave, like the input, the amplifier must be tuned to a very narrow band. Therefore, its use is limited to applications where only a single frequency sine wave is to be amplified. Class C amplifiers cannot be used to amplify a wideband signal, such as voice or music. They are frequently used to amplify the radio frequency carrier in radio and television transmissions, and are ideal for this purpose since only a single frequency signal is present. This concludes Chapter 5. I'm Dave Brown for Teletrain.